Welcome to Module 6 of the Meggitt Sensing Systems Industrial Vibration Training Course, Diagnostics Part C. In this module, we will cover electrical problems, flow-induced problems, lubrication-related problems, and belt or chain problems. To understand how electrical motor issues manifest themselves in the vibration world, it is important to first understand the components that make up an electrical motor. An electrical motor is made up of a shaft to which the rotor is mounted that rides on bearings. The rotor assembly will rotate within the stator. A stator is a part of a motor housing that has laminations which make the slots that are used to fix the stator windings. The windings are a series of wire bundles in a stator slot that create groups or phases. We also have stator poles. Poles are windings in the slots that are combined to provide a north-south field set. Poles are typically in pairs such as 2-pole, 4-pole, or 6-pole motors. Line frequency is the frequency at which the alternating current, or AC current, electrical power is delivered or transmitted. In the United States, this is at 60 Hz. In Europe, this is at 50 Hz. Many electrical problems involve line frequency or a multiple of line frequency. Synchronous speed is the speed of a motor without slip. Slip is the difference between the synchronous speed and the actual speed of a motor. We can calculate synchronous speed by multiplying 120 times the line frequency divided by the number of poles. In the United States, a synchronous speed can be calculated by multiplying 120 times 60 Hz divided by the number of poles. For a 2-pole motor, the synchronous speed would be 3,600 RPM. 2 times line frequency is generated by the number of poles pulling on a given rotor location during one full rotation. A 4-pole motor operating at 60 Hz rotates at 1,800 RPM. So to determine 2 times line frequency, we take 1,800 times 4 poles and get 7,200 CPM or 120 Hz. A 2-pole motor operating at 60 Hz rotates at 3,600 RPM. Our 2-time line frequency can be calculated by taking 3,600 RPM times 2 poles, and we get 7,200 CPM or 120 Hz. With variable frequency drives, the motor speed is controlled by varying the frequency of the applied voltage. The same principle is applied in that the 2 times line frequency vibration is created by the number of poles pulling on a rotor at a given location during a full revolution. A 4-pole motor, in this case operating at 58.5 Hz, rotates at 1,755 RPM. So to calculate 2 times line frequency, we multiply 1,755 times 4 poles to get 7,020 CPM, or 117 Hz. Stator problems can manifest themselves in the vibration spectrum in several ways. The presence of pole pass frequency, which is the number of stator poles times the slip frequency, can indicate a problem with the stator. When a problem exists with the stator, typically there will be elevated levels of 2 times line frequency. The amplitude of this frequency can be a key indicator of the problem's severity. When a stator is eccentric, it will cause an uneven air gap to occur. This will cause elevated levels of 2 times line frequency and hot spots to occur on the stator. Shorted laminations can cause excessive heating and ultimately stator distortion. Loose or open rotor bars will generate rotor bar pass frequency and possible harmonics in the spectrum. The highest amplitudes are typically 1 times rotor bar pass frequency or 2 times rotor bar pass frequency. It is also very common to have sidebands around rotor bar pass frequency spaced at 2 times line frequency. Cracked or open rotor bars will cause elevated levels of vibration at running speed and possibly at its harmonics. There will likely be sidebands around the rotational speed harmonics spaced at pole pass frequency. Variable air gap is an uneven air gap between the rotor and the stator. This is typically caused by an eccentric rotor, misalignment, or soft foot. The spectrum will show elevated levels of 2 times line frequency. It is typical to see sidebanding around 2 times line frequency spaced at pole pass frequency. Phasing can be caused by loose connectors. This can be identified in the vibration spectrum by elevated levels of 2 times line frequency with amplitudes as high as 1 inch per second. It is typical to see sidebands around this frequency spaced at 1/3 line frequency. When this condition exists, the connections must be repaired. Direct current or DC motors work slightly differently than an AC motor. The components that make up a DC motor are also different. A DC motor will have an armature mounted on a shaft that rides on bearings. There is also a commutator mounted on the shaft which has brushes that ride on the commutator. The armature assembly rotates within the core windings. A DC motor has an SCR firing card which receives a speed reference. The SCR card then provides power to the armature through the brushes which feed the commutator. The core is also energized to create a magnetic field. A speed and current feedback loop is created, sending signals to the SCR card to adjust the power being provided to the armature. It is normal to see a vibration peak at the SCR frequency during normal operation. The SCR frequency will depend on whether it's a half-wave or a full-wave rectified motor. For a half-wave rectified motor, the SCR frequency would be 3 times the line frequency. For a full-wave rectified motor, the SCR frequency would be 6 times the line frequency. The amplitude of the SCR frequency is usually low, and there should not be any other multiples of line frequency present in the vibration spectrum. Damaged armature windings or grounded windings will show elevated levels of SCR frequency, or 2 times SCR frequency. Additionally, you will likely see a peak at 1 times line frequency. When an SCR firing card fails, a portion of the power going to the motor is lost. This loss in power causes a momentary change in speed. The momentary change in speed will generate a vibration response at 1/3 SCR frequency and 2/3 SCR frequency. A defective SCR or loose connections can generate many frequencies related to line frequency and or SCR frequencies. The sheer presence of 2 times line frequency, 4 times line frequency, or 5 times line frequency is an indication of a problem. Often, 1 times line frequency or 5 times line frequency will be elevated. Fluting is a condition that occurs when an electrical current is passed through a bearing during operation. Fluting is typically caused by improper motor grounding and will show up in the vibration spectrum as seemingly random, very high-frequency events. The spacing of these high-frequency events is a key indicator and will be spaced at ball-pass frequency outer race or ball-pass frequency inner race or both. The acceleration G levels can be very high and can be easily missed with routine data collection. Fluting can often be heard. In some cases, if properly trended, this damage can exist without failure for a significant amount of time. Blade or vane pass frequency is the number of blades or vanes times the RPM of the machine. This frequency is normally present in the data for pumps and fans. It can be problematic if it coincides with natural frequencies of the system. Large amplitudes of these frequencies can indicate a problem. Flow turbulence can occur in both pumps and fans. With pumps, turbulence can be created by piping sections that are too short. With fans, turbulence can be caused by variations in the airflow. Flow turbulence will generate random low and high frequency vibrations. Cavitation is the presence of air bubbles that collapse in the pump housing. This is created by a low suction pressure or too little material to the pump. Cavitation sounds like gravel going through the pump and can be very damaging if left uncorrected. Lubrication problems are not easily identified with traditional vibration techniques. A lubrication problem will manifest itself in the 10 kHz to 40 kHz range. Specialty measurements such as HFD, peak view, and shock pulse can provide an indication of a lubrication-related problem. Over-lubrication does not tend to generate a distinct vibration response, while under-lubrication can generate high-frequency, seemingly random vibration that is often not much higher in amplitude than the noise floor. Worn or loose belts will often generate several harmonics of belt frequency. Often 2 times belt frequency is the predominant frequency. Belt frequency can be calculated by multiplying 3.142 times the RPM times the diameter of a given shaft divided by the overall belt length. Misaligned pulleys will generate a vibration at rotational speed of the driven or driving machine. Typically, the highest levels are in the axial direction. It is common that the predominant frequency at a measurement location is the running speed of the mating shaft. For example, the highest measured vibration on a motor can be the fan RPM, or the highest measured vibration on the fan can be the motor RPM. An eccentric pulley will generate elevated levels of vibration at 1 times the eccentric pulley's RPM. Generally, the vibration will be highest in the radial direction and can be present on both the driven and the driving machines. Belt resonance can cause elevated vibration, especially if it coincides with the running speed of one of the pulleys. This vibration can be corrected by changing the belt length, the pulley diameter, or in some cases tensioning the belt. You have just completed Module 6, Diagnostics, Part C. Please join us again for Module 7, Diagnostics Part D. You can visit us anytime at www.wilcoxon.com or contact us directly at 1-800-WILCOXON.